Hey everyone, Houston Math Prep here, continuing in our linear algebra series from our video on elementary row operations, now moving on to the row reduction algorithm. This algorithm is a procedure that allows us to use any of our 3 elementary operations from our last video to systematically transform a matrix into an equivalent matrix in one of the echelon forms. We've got a reminder here that our 3 elementary row operations are swapping 2 rows in the matrix, multiplying a row by a non-zero constant, and adding multiples of rows to other rows. What we're going to do is work through 2 entire example matrices in this video. Our first one is pretty standard looking here. You'll see that later on our second example is a bit less ordinary. We're going to look at the row reduction algorithm in 2 main phases. The first phase is the forward phase of row reduction. These 3 steps listed here on the right half of the screen will get our example matrix into echelon form. Once we've done that, then we'll show you the other phase of the algorithm that transforms it into reduced echelon form. But for this part of the video, the forward phase will basically be focusing on entries in our matrix and working from left to right during this phase. Notice our first step here says to start with the first non-zero column, so first we need to identify that. Looking at our first example, you can see that our first column here is definitely a non-zero column, so we'll be starting with that. It says, if necessary, swap rows of the matrix so that a non-zero entry is in the first row. For our example here, we don't have a 0 in the top entry of this column, so we're good to read on. Notice that it says this column we're looking at now is going to be a pivot column. Remember, that means it's going to have one of our lead entries in the matrix. So we didn't have any tasks to perform from step 1 based on how our original matrix is set up here, and that's okay. Let's move on to step 2. We need to use replacement row operations to get a 0 entry in all positions below the pivot. So here our top entry of 1 is our pivot. It's going to be our lead entry in the first row. And we want to start working down this first column to get zeros in every spot below this pivot. So we start to think about how many copies of row 1 will we need to add or subtract with row 2 to make this first column entry here into a 0. We'd need a -2 to add to the +2 that we have in order to make a 0. So how many copies of this pivot of 1 will do that? Well, we'll multiply it by -2, and then we can get our 0 that we need. So we'll be taking row 2 and subtracting 2 copies of row 1 from it. Here's our row 2 that we're trying to create a 0 in, and below it we've got our row 1 multiplied by -2. You can see that adding these together gives us a 0 entry in the position we wanted. If you look at our notation here up above, it says that once we do this operation, we're going to store that new row we created in the row 2 spot of our matrix. The reason being that's where we're trying to create a 0 entry in the first place. Remember, we're working on step 2 over here, which is to create zeros in all entries below our pivot. So we've got one of them finished, and now we just need to work on this entry of 4 to finish our first column. So let's take our new matrix and put it back up at the top so we have room to move on. We'll be doing the same idea with this bottom entry now. How many copies of row 1 will we need to add or subtract with row 3 so that the 4 becomes a 0? And this time we'll need to subtract 4 copies of row 1 in order to turn that 4 into a 0. So we'll take row 3 and subtract 4 times row 1 from it. And since we want our 0 in the bottom row this time, we've written that we'll be storing our new row in the row 3 slot. So we write down row 3 and -4 times row 1. When we add those together, we get a 0 in the first entry, like we wanted. And now looking back at our notation, remember we said this is going where our old row 3 used to be. So we drop our new row 3 into our matrix, and we should be starting to feel pretty good about ourselves at this point. If we look at what we've got now, we've transformed all the entries below the pivot into zeros. And so our step 2 of the process is now complete. Moving on to step 3, it says to ignore the pivot row and all rows above it. Since that was our first row we worked on, there's nothing above it. And now we repeat steps 1 and 2 on the remaining part of the matrix that's left when we ignore that row. So if we look at step 1, it says to start with the first non-zero column. Now, since we're ignoring the first row, the part of the first column we're still paying attention to is all zeros. So we'll be focusing on the next column over. You'll notice that we don't have to swap any rows to get a non-zero entry into this top spot here. We've got a -3. And this -3 will be our new pivot entry to work with. Now, step 2 of the algorithm sends us back to making zeros below our new pivot. The nice thing with this column is that there's only one entry below the pivot of -3, so we just have to find a way to turn this -6 into a 0 entry. Think about how do we use copies of row 2, the pivot, to turn this -6 into a 0? Well, we can reduce a -6 with a +6, so if you think about what to multiply -3 by to create a +6, then we should come up with -2 times that second row. So our notation says we're taking row 3 that we're changing and subtracting 2 copies of row 2 from it. Again, that's the same thing as thinking of adding -2 copies of row 2, so however you keep that solid in your mind is just fine. And we'll be replacing row 3 with whatever we get. Here's our row 3, and below it we've written -2 times row 2. So now we'll add these together and get a row that has a 0 exactly where we wanted. We'll then drop that result in as our new row 3 for our matrix. You can already see the progress here, but let's copy this back up to the top and refer back to our algorithm. So step 2 had us obtaining zeros everywhere below our pivot in this column, and since this entry was the only entry below our pivot, we're now finished with step 2 again. And of course, you recall that step 3 will have us ignore the row we just worked on and everything above it as well, and repeat the first 2 steps again. If you look at what's left, we have a single row remaining. And so the first non-zero column in this case is just the first entry we get to that's not a 0. For this row, it's the -3 entry here. If we were to try and repeat steps 1 and 2 again, we would notice there are no entries below this pivot to transform. So there's really no work remaining to be done for steps 1 and 2 in this case. And this means we've completed this forward phase of the row reduction algorithm. If we take a look at our transformed matrix, we'll notice that it's now in echelon form. In each non-zero row, the leading entries are all to the right of any leading entry in a row above them. We've got zeros below all leading entries. If for some reason we had a row that was all 0 entries, we could move it to the bottom, but we don't have that in this one. At this point, we might choose to just work with this information, use this echelon form, find solutions for other variables, working upward, back substituting each time. So all of our work so far in the algorithm, we said was our forward phase. Getting it into echelon form had us essentially working from left to right column-wise, and in each column we were working downward within that column from the pivot. If we want to go further and transform our matrix into reduced echelon form, we have an extra phase of the algorithm, which is sometimes thought of as a backward phase, to make this happen. In this phase, instead of working left to right and mostly downward, we'll actually be working from right to left using the pivot entries and generally working upward. If we look, it says to start with the pivot farthest to the right, and if you remember from our previous video on echelon forms, the reduced echelon form needs us to make all of the pivot entries have a value of 1. So you can see in this part of the algorithm, this is where we take care of that. It says to scale the pivot to make its value 1. So the pivot farthest to the right is the -3 in the bottom row. We need to scale that to make its value 1. So one distinction we want to draw here, we are scaling. That means multiplying a row by a real number to change the values. When we were creating zeros in entries, that's when we were adding copies of rows to other rows with replacement. But to create an entry of 1 where it's needed, we'll just be multiplying a row by a number. To make this -3 into a +1, you can think of multiplying by its reciprocal of -1/3, or you can think of it as divide by -3. That'll turn our -3 into a 1, and our -9 becomes a +3. Of course, our zeros stay the same, so we're not undoing any of the progress we made in the forward phase before. So that will give us a changed row 3 with an entry of 1 where we need it. Let's copy that back up to the top, and we'll move on to the next step. Next, we want to create zeros above our pivot entry. We'll do this the same way we did it in the forward phase by adding copies of the row that contains the pivot to other rows. going right above the pivot to this -3 entry, if we need to make that into a 0, we would need to add 3 copies of this pivot to it. So we'll take row 2 and add 3 copies of our pivot row, row 3, to it. Again, actually replacing that row 2 with our result here. So our row 2 is 0, -3, -3, 3, and 3 times our row 3 is 0, 0, 3, 9. We will add those together, gives us 0, -3, 0, 12. So when we replace our row 2 with this, you can see we get a 0 right above the pivot, just where it was needed, and now we'll just need to reduce the entry of 2 in the top row, and we'll be good for this column. Let's move this up to the top and focus on that 2 entry. So if we're trying to reduce the 2 to a 0, and our pivot entry here we're using to do it is a 1, then we will need to subtract 2 copies of that pivot row in order to do just that. So let's replace our row 1 with the result of row 1 minus 2 times our pivot row, row 3. Here's our first row of 1, 4, 2, 1, and we'll go ahead and multiply row 3 by -2, and then we can add those together, getting 1, 4, 0, -5, and that's going in as our new row 1 in the matrix. So we'll replace, and see that we have sought after zeros for each entry above our pivot in the 3rd column now. If we look back at our instructions, you can see that we've created zeros above the pivot, and now we simply need to repeat what we just did with each remaining pivot column working toward the left. So our next destination is column 2, and our pivot there is currently showing as -3. Remember that the first thing we'll do with any pivot entry in the backward phase of the row reduction algorithm is to scale it to a value of 1. So we can scale this pivot to a value of 1 by dividing by -3 or multiplying by the reciprocal of -3 if we prefer. Dividing row 2 by -3 leaves our zeros the same, and it gives us a 1 and a -4. We'll now use that pivot value of 1 to work on the entry above it. The only entry above this pivot in our matrix is our +4 entry. So using that pivot of 1 to reduce that 4 to 0, we would need to subtract 4 copies of the pivot row from row 1 to make that a 0 entry. So in row 1, we'll be replacing that with row 1 minus 4 times row 2, our pivot row. We write down our row 1, and we'll use -4 times the pivot row. Adding those together gives us a row that reads 1, 0, 0, 11. And that will be our new row 1. Here we have our 1, 0, 0, 11. So after that single replacement, focusing on column 2, we have every entry above the pivot, just the 1 entry, as a 0 entry. This means we're finished. It's time to move on to the remaining pivot column. You'll notice that this pivot entry is at the top of its column, so there aren't any remaining entries above it to transform. This means we're finished with the backward phase of the algorithm, and you should be able to see that our matrix is now in the reduced echelon form. Here, if we interpret this as an augmented matrix for a linear system, we can read that our solution has the first variable from our matrix equal to 11, our second variable equal to -4, and our x3 variable equal to 3. For our next example, we're going to use a slightly less conventional looking matrix to begin with. We'll assume that you watched our last example, so we won't be explaining quite as slowly here. We'll more so be focused on how this example is a little bit different than the typical case as we go. We'll begin with our forward phase working toward the echelon form. So the first step says to start with the first non-zero column. In this matrix, we don't have any completely zero columns, so there's no worry there. But we do want to pay attention to what's going on in our first column in the initial setup. Since we have a 0 entry in the top spot, we'll first need to swap that first row with another row that has a non-zero entry in that column. Here I'll just go ahead and choose row 2. You could swap the first row with row 3 if you prefer, that would be just fine, but I'll use row 2. So swapping that gives me a 1 in the top spot, and the row with the 0 drops down, and this is going to be our first pivot column. One nice thing about moving on to step 2 now is that we've already created one of the 0 entries we needed below our pivot as part of the first step of the algorithm. So that's a minor bonus there. We'll just need to focus on reducing the 2 entry at the bottom of the column to a 0, and to do that using the pivot row, we'll subtract 2 times that pivot row from row 3, and we'll replace that bottom row with it. So taking row 3, the row we're changing, and multiplying the pivot row by -2 means that when we add them together, we get that 0 in the first entry of the row like we wanted. Now don't be too alarmed here. You'll notice that we also created another 0 in the entry next to it. That'll just happen sometimes, but if we stick to the algorithm, it'll all work out. So our first column has all zeros below the pivot, which means that our step 2 is complete for this column. Our step 3, remember, says that we'll now ignore that row we worked with and any row above it if there are any, and we'll repeat that process with the part of the matrix that's remaining. So step 1 now has us look for the first non-zero column. Notice that the first 2 columns are 0 columns. They have zeros in all entries. And so the next pivot column will actually be our 3rd column here. We don't have an issue where there's a 0 in the top spot. So we can keep this 1 at the top as our pivot and reduce what's below it. If we want to reduce the +1 in row 3 by using our pivot that's also a +1, we'll simply alter the bottom row by subtracting the pivot row from it. So if we take row 3 minus row 2, it leaves us with 0, 0, 0, 2, -8, and 12, and we replace our row 3 with that. Notice that everything below our pivot entry is now 0, and our work in column 3 is complete for the forward phase. Referring to step 3 of the algorithm, we now ignore that pivot row and everything else above it and repeat with any remaining pivot columns. Since our next pivot is in the bottom row, there are no zeros to obtain below it, and we have no tasks to complete in this column. So after working on each non-zero row, we're finished with the forward phase, and our matrix is now in echelon form. What you might notice about this echelon form, we have no pivot in column 2. We also have no pivot in column 5. So this is a nice echelon form, but it looks a bit different than our last example, where every column but that last column had a pivot entry. Let's now begin our backward phase of the algorithm. I'll put up the instructions for working right to left here. If we look for the pivot that's farthest to the right, you can see it's definitely the 2 in the bottom row, so we'll start by scaling that row so that the pivot is a 1. We can do that by dividing the row by 2 or multiplying by 1/2. Again, remember that creating 1s for the pivot entries is about multiplying a row by a number, not adding copies of other rows to it. So dividing the last row by 2 gives us a 1 for that lead entry there, and we'll start to use that 1 as our pivot to get zeros for all the entries above the pivot. Remember, the backward phase is about getting zeros above the pivots. Working up this pivot column, we'll first create a 0 where the -3 is located. We'll do that by adding 3 copies of the pivot row to row 2. Here we have row 2 plus 3 times row 3. We'll add those together. And since we want to replace the -3 entry we had above the pivot, this replacement will be going in as our new row 2. So we get 0, 0, 1, 0, 0, 5. Putting what we have back at the top, the only thing left to do in this pivot column is to reduce the +2 entry at the top. So we want to change row 1, and we'll subtract 2 copies of the pivot row from row 1 to make our needed 0 entry there. On top we have row 1, on the bottom we have -2 times row 3, and adding those together gives us a new row of 1, 1, -2, 0, 1, -12, which replaces our previous row 1. Taking a look at where we are now, everything above our pivot in this column is a 0 entry. So our work in this column is done, and we'll move to the next pivot we have to the left, which is the +1 entry in row 2 in the 3rd column. Fortune has smiled upon us a little bit this day. Since the pivot is already a 1, we don't have to worry about scaling that row that it's in, and we can just get straight to creating a 0 entry above that pivot. To make that -2 into a 0 using the pivot below, we'll need to add 2 copies of our pivot row to row 1. So 2 times row 2 is 0, 0, 2, 0, 0, 10. And adding those together gives us 1, 1, 0, 0, 1, negative 2 for our new top row in our matrix. We've obtained our 0 above our pivot in this column, so we are ready to move to the next pivot column. Our next pivot column looking to the left is the first column, and that pivot is at the top of its column, so there are no entries above it that need to be reduced to 0, which means our backward phase of the algorithm is finished, and we have our reduced echelon form for the matrix. Keeping in mind the concept of a linear system of equations and thinking of this as an augmented matrix for a system, let's imagine what these 3 rows would actually say as equations. Our first row would read as x1 plus x2 plus x5 is equal to negative 2. Our second row, this is the third column here, so that would be x3 is equal to 5. And our last row would say x4 minus 4x5 equals 6. So you can see that we don't just get specific numerical values for the solution of all of our variables. We get a specific value for our third variable, right? Here it tells us that x3 is equal to 5. But all the other variables in our system seem undetermined somehow. What we'll need to keep in mind when solving a system that some variables might have specific values and some variables might depend on other variables for their values. And it's sometimes the case that part of the solution is that variables might be allowed to take on any value. How we interpret the solution for all of our variables in a situation like this comes down to the idea of what is a basic variable and what is a free variable in our system of equations. Our next video in this linear algebra series explains the difference between these and what it means for our solutions. Thanks for your patience with row reduction. We'll see you in the next video.